Fusion is exactly the opposite process of fission. So in fission, the neutron absorbed by the uranium splits the uranium from one big nucleus to two smaller nuclei and some neutrons. In this one, you're going to try and fuse them and push them together, okay? All you need is the hydrogen nucleus, which is literally just a proton, okay? You take two protons and you force them together, alright? The problem with this is, if you have a proton and a proton, you have two positive particles, and the electrostatic repulsion between them is enormous, right? The strength of a proton and a proton is near impossible actually to overcome in a power station, for example. Okay? The only time you actually see this happening naturally is in the center of a star. So this is the reason for a star being able to survive and keep burning basically for about however many, 13 billion years. Okay? So take a proton and proton. If you have enough, you need high pressure, okay? You need high temperature to overcome the electrostatic repulsion between them. And if you do, what happens is you put the two particles, the proton and the proton together, and one turns into a neutron. Now back to chapter 6, when a proton turned into a neutron in beta-positive decay, what has to be created in order to balance? A positron has to be created, so you get a positron created as well. Okay? So your charges are balanced. And then what can happen is you take another proton, separate proton, put it together with the proton-neutron that's just been produced, okay? And then you end up with three particles, proton, proton, neutron. Okay, this is a helium isotope. And what is also produced in this section here is gamma radiation. Okay, so energy. So the second one, you take your proton and your neutron, which is a hydrogen 2. So this is just an isotope of hydrogen, 2, 1. You put another separate proton in there with it, and then you have a helium 3, 2, so 3 mass number, 2 charge number, and gamma is produced as well. Okay? The energy produced in fusion, okay, is much greater than fission. Alright, the energy produced in fission, remember, was because there was less mass after, so the mass had to turn into energy. In a fusion reaction, which is simply proton-proton, put them together, high pressure, high temperature, produce another hydrogen atom where the proton turned into a neutron or a positron, then take another proton, put it with that hydrogen, and create a helium nucleus and gamma. The amount of energy produced in a fusion reaction is way more than you get from fission. So why don't we use nuclear fusion all the time to produce our electricity? Why don't we use this energy to heat a coolant, produce steam, turn a turbine? Okay? The difficulty is, and if the question is, why is it not used? First of all, they have done this successfully. Alright? There are fusion reactors in the world. Okay? They have been switched on. They have successfully fused protons and protons to create this energy. But the problem is, so they've come up with how can I get the high pressure and high temperature that I need without it melting a material? Okay? And the way that they got around that was, instead of letting the protons and all the hydrogen nuclei in the reactor just kind of orbit or spin around the reactor itself and touch the sides, if it got too hot, it would melt the reactor. Okay? What they did was they just used magnetic fields and said, well, we're not even going to let the protons touch the reactor. We'll use magnetic fields to keep them inside, and we'll build up the temperature and pressure without it melting the reactor itself. So they've done that. They have successfully achieved fusion. The problem is they can't maintain it. Okay? So producing nuclear fusion is not the issue. Maintaining nuclear fusion is the issue. If the question says, why is nuclear fusion not used on the large scale, or is it not used to produce electricity around the world? Very high pressure and temperature is required. We know that. The reason that you need very high pressure and temperature is to overcome the electrostatic repulsion between protons, okay? And it is very difficult to maintain, or too difficult to maintain at the minute, okay? So it's maintenance, it's not producing it, it's maintaining it that's the problem, alright?